All right, there we go. So now we're doing number 1. There we go. And for those of you just tuning in, this is our issue. We got to figure out how to deal with that. All right. So, is everybody good with kind of what I did here? That the density is the amount of mass per unit volume, and the per unit volume can be written as the cross-sectional area times some dx. Follow? Okay. So, I guess we can. So, do you guys understand that the r and the x are kind of interchangeable? Does that make some intuitive sense to you? Because you're just measuring the distance along the x-axis, right? Okay, so I'm going to use everything dx, okay? So, if I rearrange this then, this gives me that's supposed to be an arrow, gives me the dm is what? Rho a dx, right? Good? Okay. Oh, right. Okay. Okay. So, and then the problem told us that rho is, here was why I got tangled up, it's rho o times x, right? So the idea is this is just some constant. It's like the slope of your density line. Okay? So I'm going to do one more substitution to get this. dm equals rho naught times a times x dx. Follow? All right. Now, if I lost you with this changing the dv to a dx, basically what it boils down to is you can treat that volume density the same way that we treated linear density when we did center of mass. Okay? It boils down to being exactly the same thing. So if you wanted to, you could replace this with lambda and lambda naught, and it would still work. Okay, so are we good up to here? All right, so great. So where do we go from here? So, like Alex said, our rotational inertia is just the integral, it's a super trivial calculation, of r squared, but we decided we were going to use x, so I'm going to write x squared dm, right? Follow? And so now I can substitute this mess in for dm. Oh, darn it. Why does it hate me? Oh, because it's not calibrated. Where did all of my work go? Did I delete it by accident? I totally did. So there's that. I want to be here, and I want to put in a blank page. Why won't it put in a blank page for me? Blank page. What? This is going to be like, duh.
Click on the page.
Ah. Thank you. That was embarrassing. I know AV physics, but I can't work a computer. Okay, all right, so is everybody good with what we've got here? All right, so all I'm going to do is I'm going to rewrite this, but I'm going to replace dm in. So I've now got I equals the integral of, notice I'm going to have x squared times this max, so I'm actually going to get x cubed, right? So x cubed times whatever rho o is times whatever the area is dx, right? And we're integrating from 0 to our length L. Let me pause for a minute. I heard a disgruntled sound a moment ago. Talk to me about your disgruntledness.
The x cubed? X squared times x.
Yeah.
Yeah.
Good? All right. So all of this garbage here is just a constant. That doesn't affect anything, right? So just leave it there. And then what's the integral of x cubed? 1/4 x to the 4th, right? So this is 1/4 x to the 4th rho o a evaluated between 0 and L. So plug in your L, and you end up getting, this. You get 1/4 of L to the 4th times rho o times a. Great, there's I. But that's not one of the choices on the sheet. So we need to think about something. Somehow mass is hiding in here somewhere, right? Somehow the mass has something to do with this. And I'm looking at this, and let's see, this is density, so that's mass per unit volume, right? And I got A, and so I ought to be able to do something here and find a way to get my mass back in there. Okay, and so here's where the hint comes in. All right. So the little hint that I gave you guys was I told you, remember that when we did center of mass, one of the things we learned was, and this is weird, you can write mass as the integral from 0 to m of dm. Which is, it seems silly, right? Does that make sense? This is, I think that's like a fundamental theorem of calculus or something. There's a name for that, but it's a thing. Okay? And don't quote me on the name of that theorem. I'm not positive that's the name of the theorem, but it's a thing. What's that? Oh, okay. All right. So look, though, we know what dm is, right? So this is the integral of, well, dm was, what was it? It was x times rho naught times a dx, right? And now I'm going to integrate from 0 to L. Right? Because that's the length of my rod to get the whole mass. Right? Because I'm now integrating according to x. So I have to get to the length of L before I get my total mass. Good or no? Right? So we're almost done. So now we integrate this thing. So what's the integral of x? 1/2 x squared, right? So this becomes 1/2 x squared times rho naught times a evaluated between 0 and L. So plug in L, you get 1/2 L squared rho naught a is my mass. So we are like 99% of the way done. So let me pause for a minute for the questions about what we've done here. All right, so now all I got to do is figure out how many times this goes into this. So, well, look, isn't this the same as 1/2 L squared rho naught a? Let's see, so what do I have to multiply this by to get that? Well, I need another 1/2. I need another L squared. Oh, and this is m. Oh, so it's 1/2 m L squared. Yeah, wow, right? It's a kick in the teeth, I hear you. So, I think in the last 10 years I've seen one year where the AP test had you do something like this. So it does come up from time to time. Probability of it isn't super high, but it does happen. Right? Yeah, Alex. I'm not sure. I'd have to see where you went from there. I am worried that you inadvertently treated it as a, I don't know, I'd have to look at what you did. Because it should not have worked. Because if you do this, you should get 1/12 ml squared, not 1/2 ml squared. I don't know. Can I look at it at the end of class? Is that all right? Okay. All right. Yeah.
If it around its less distance, because when you take the interval from 0 to L, that's to its farthest point, right? So that's the densest end. So how is this giving you the British ownership of the less dense end?
I gotcha. So just so we can sort of picture this thing, this is not visually what I'm about to do is not accurate. But the idea is you've got a rod. So here's your number line, right? So this is x equals 0, right? And the idea is it's getting more dense as you go that way. So there's our shape. It's not technically it's not getting thicker, but it's getting denser. Okay? And so the idea is we're integrating from a radius of 0 out to a radius of L. That didn't answer your question, did it?
Step would be 0 to L. So if we're integrating from 0 to L, wouldn't that give us
No, because you're treating the position at 0 as the less dense end. So you're rotating it about this point. So like if you imagine this thing rotating, this thing is going to have a radius of rotation of L, and the less dense end is going to have a radius of rotation of 0,
Okay.
thus indicating that that's the point that you're rotating about. Follow? Everybody? Okay. Cool. Questions on this, you guys? I don't know. It's up to the people who write the AP test, not up to me. All right. This is a really big trick, you guys. I've seen that come up in a number of different scenarios. So tuck that in your back pocket, I guess. All right. So we good? I don't know. Is that right? Oh, did I?
No, you're good. Don't touch it.
I'm not touching it. Watch me not touch it. All right. So while that's happening, because this whole mess here is M, based on, right? This is M. So this mess is this mess. That's M. Cool. So you get M times 1/2 L squared minus 1/2 M L squared. Good, you guys? All right. Okay, so numbers 2 and 3, like I say, I think it makes sense to do one of these, but maybe not necessarily both of them. They're both very similar. Number 3, I will say, is worded poorly. So let me clarify what number, maybe we should do this. Maybe we should do number 2, and let me clarify what number 3 was asking for. So number 3, you're not, so it says, if the string does not slip, this is the last sentence on number 3. It says, if the string does not slip, then as the mass falls and the cylinder rotates, the suspension holding the cylinder holds up on the mass with the force of blah, blah, blah. So what you're actually looking for in question number 3, what you're actually looking for in question number 3 is not, as I originally thought, oh, where's my drawing? Oh, there is no drawing. Super. Super duper. That's recorded too. All right, so the drawing looks just like number 2, right? We've got this disc with a thing, there's a mass hanging from it, it's being suspended from the ceiling, right? So when I first read it, I thought we were looking for the upward force on this hanging mass because it says pulls up on the mass. But it's not talking about that. It's talking about the force that this thing that's suspending the whole shape, it's talking about the force that exerts. Okay? So this little triangle thing that's holding up the pulley is providing enough force to support the weight of the pulley and this tension force. Does that make sense? There are 2 downward forces on the pulley itself. There's the force of gravity on the pulley and the tension from the string. So that means that the support force has got to be big enough to cancel those 2 things out. Does that make sense? So you got to find your tension, and then it's one more step beyond that, which is adding it to the weight of the pulley. Was that not, I think, not clear for the wording of the problem? It was sketchy, I know.
But it wasn't sketchy because it wasn't sketchy.
Oh, very good, very good. All right, so that's the deal with number 3. So, with that in mind, why don't I do this? Here, so the answers for both 2 and 3 are B. They're both B. So, I'm sensing some discontent. Was that about 2, 3, or both? We're going to do one of them. Who would prefer to do number 2 right now? 1, 2, 3, 4, 5, 6, 7. Is that a, okay. Who would prefer to do number 3 right now? Oh, wow. It's close. 1, 2, 3, 4, 5, 6. Okay. So, those of you who voted for 3, did you get 2 right?
Yes, except I got G squared.
Okay, that sounds like it's probably just an algebra mistake somewhere. You probably just got to cancel one somewhere. Those of you who voted for 2, did you get 3 right?
Yeah.
Yeah?
I cross-referenced this.
Ah, I got it. Did you Google search on it? All right. I gotcha. All right. So like I say, the two problems are very similar. I'm gonna go over number 2. Here we go. Let's do it. Okay, so here we go. Number 2. All right. So here's the deal with number 2. We've got this pulley system with a 16 kilogram block hanging from it. All right. So here's what I know. I know the rotational inertia of the flywheel, that's this thing. I know the rotational inertia of that thing is 0.5 kilogram meters squared. I know that the mass of this thing is 16 kilograms. I know the diameter of the wheel, which is stupid, so I'm just going to chop that right in half, and the radius is 0.2 meters, right? And then it says when the block is released and the cord unwinds, the acceleration of the block is what? We got to find it. Okay? So, there are 2 unknowns in this problem. Okay? There's the acceleration of the block and the tension in the rope. Okay? So we need to come up with 2 equations to solve for those. All right? So let's do this. First of all, let's look at the 16 kilogram block. So if you look at the 16 kilogram block, what forces are acting on it, you guys? Gravity. So my gravity is just going to be 16 times g, right? Follow? And there's tension, Ft. So I think I can come up with an equation now using this and acceleration, right? Because my net force should be 16g minus Ft. That's got to equal my net force. And my net force is mass times acceleration. Follow? So that's one equation with 2 unknowns, right? This equation includes my tension and my acceleration. G obviously the constant. Good? All right, so where's the other equation going to come from, you guys? From torque, from the wheel. Right? So if I focus on the wheel, then my tension is going to provide the torque, isn't it? Okay? So it looks like the tension from the torque is equal to my net torque, right? So I can write it 2 ways. I can write it as I alpha, or I can write it as tension times radius. Make sense? So what I need to do is I want to write either an equation for tension or an equation for acceleration. All right? So what I'm going to try to do is I'm going to try to see if I can come up with an expression for tension in terms of acceleration. And then I can plug it in here, and I'll have one equation that just has A in it. Follow? So I'm going to solve this mess for tension. Okay? So if I do that, look what I get. I get tension equals I alpha over R, which is warm, except it doesn't have acceleration in it. So,
AR.
oh, but A is alpha R, right? Which means the alpha is A over R, right?
So it's,
Is that right? Why am I uneasy about that?
is it IA over R?
Yeah, it's I over
Yeah, that's right.
Oh, right. Yes. Yes. Totally. 100%. Thank you. That was what I was looking for. So Ft is I, and then my alpha becomes A over R, and then over R, you're right. You get A over R squared. Thank you. I was worried. I was thinking the hours canceled.
I just said that.
All right. Everybody good? Okay. So from here, so I will say that, so in number 3 is solved almost the exact same way, except the mass of the hanging thing isn't 16, it's some other number. But otherwise, you still come up with these same 2 equations, and then you just solve for whatever the missing thing is in number 3. I think there you're solving for tension instead of acceleration, right? Okay. So, here we go. Look at me using the smart board. All right, all right, so close. So now all I'm going to do is I'm going to take this equation for tension here and plug it in up here, and then I'll have an equation that just has A in it. So I'm looking at 16G minus this mess, IA over R squared, equals 16A. And now plug in your numbers and solve for A. Do I need to go through that part of it? Is that okay if I end off here? We know everything in there except for A, so plug in your numbers and do some algebra. Cool? Alex? Say that again. Oh, could you get the acceleration of gravity?
Could you gather the gradient gravity?
No. Well, and you couldn't get exactly acceleration of gravity either, because that wheel has rotational inertia. You need some torque to turn it exactly. Now remember, early on in the class, all of our pulleys were massless. That's why, because early on we hadn't learned about torque yet. Follow? I know, right? Those are the good old days, massless, frictionless pulleys. Now they're just frictionless. But not that I know of, no. You can do that though. It would just be an additional friction force. You'd have to know the radius of the axle and. Okay. Massless, frictionless. All right. Are we good, you guys? All right. I will say this thing here, you guys. This thing seems to come up a lot, where you have to set up a system of equations, one determined by a force on a block, and one determined by the tension on the, or the torque on the associated pulley. I said that weirdly, but this comes up a lot. So, cool? All right. Questiones? All right. So, let's see if we can't finish up the last little chunk of notes. And you guys, go home and see if you can do number 3. It's similar to the yeah, right? Out. Be gone with you. Okay. All right. So let's see if we can finish up the notes from yesterday. Honestly, I don't think we can. I think I did not do a great job splitting this up into bite-sized chunks. But let's see what we can get through. All right. So real quick. Yesterday I did a whole bunch of algebra and just like some stuff, right? Here's I think the important thing that you need to get out of what we learned yesterday. All right? When you have an object that's rolling, it's going to have 2 types of energy. It's going to have translational kinetic energy and rotational kinetic energy. If you take one thing away from all that stuff we did yesterday, the one thing you should take away from it is, where is it? It's on here somewhere. Is this idea right here, that your rotational kinetic energy is equal to beta times your translational kinetic energy. And what was beta? The fraction from I. So if you just took one thing away from an hour of algebra yesterday, this is it. That's the thing you have to get, because that will come up again and again and again. Cool? All right, cool. So, let's see. So where did we end off? So we did a whole bunch of algebra. We did this. We were very satisfied, or I was very satisfied that this worked out. We got the same acceleration. And that was where we ended. So, all right. So your next slide, I hope, is this one. It's got the little yellow box, and it says this same B are identical. Yes? Yes. All right. Read and think. I should have had you guys do this last night. I didn't realize this was the next page. One of those guys is going to go farther up the hill. I wonder which one. All right, so what do you guys think? Which one's going to go farther up the hill, A or B? Okay, yeah, so the idea is they're both moving along, and then they get to a hill. Okay, so they're both moving along with some velocity, and then they get to a hill, all right? And so the idea is one of the ramps is frictionless, so the ball will slide up the hill, okay? Sort of. And the other one will roll up the hill, okay? So, and that's the important thing, and that was why I said sort of when I said it'll slide up the hill. It'll slide up the hill while still rotating. Okay, do you guys understand that? Okay, so in other words, the one that has friction as it rolls up the hill, the rate at which it's spinning is going to slow down, right?
Yeah.
You guys see that? Whereas the other one is going to just keep spinning at the same rate. Like a bowling ball with backspin. That's a perfect example. Yes. Right? So which one's going to go farther? The one that has friction or the one that doesn't? What do you guys think? Who thinks that? What were the choices? So B is the one that's frictionless. So how many of you think that B is going to go farther up because it's frictionless? Ooh, how many of you think A is going to go farther up because of? That's weird. Doesn't it seem like friction should stop it? Okay. All right. So let's do this. All right. So here's ball A, right? So ball A is going to have, at the beginning, it's going to have some kinetic energy and some rotational kinetic energy, right? I'm just going to make up some garbage numbers so we have something to talk about, okay? So maybe this is 100 joules, and maybe this is 40 joules. Good? Make sense? Now, this A rolls, which means that as it rolls up the hill, it's going to lose kinetic energy, and it's going to turn slower and slower until it stops turning, right? So at its highest point, what's the KE going to be? 0. What's the RKE going to be? 0. And therefore, the GPE at the top must be 140 joules, right? Sorry, I'm using honors notation. Sorry. Are you guys cool with this? Kinetic energy, rotational kinetic energy, gravitational potential energy? So friction doesn't actually do work on it. Remember, because there's no work at the point of contact. But that's it. Right. That's the. Yeah. Where is it? Because there's no motion at the point of contact. Is that what you're talking about? Good. All right. Okay. So that's that. Now the one that slides, the one that has no friction, I guess I should say, is going to be this. It's still going to have a kinetic energy of 100 joules when it first gets there. It's still going to have a rotational kinetic energy of 40 joules. But as it goes up the hill, the RKE doesn't change, right? Because there's no friction. So when it gets to its highest point, the RKE is still going to be 40 joules. So at the point when it stops moving, what's the GPE going to be, you guys? Just 100, right? Meaning that it didn't go as high up, right? Does that make sense? In other words, this one has two types of energy which are getting converted to GPE. This one only has one type of energy getting converted.
Wait, so what would be at the top spinning this?
Right? Now, there's another explanation for this. Which direction does friction point? So look, this ball is spinning this way. If there's friction, it's going to prevent it from sliding across the surface. Which way does friction have to push to prevent it from sliding? Up the hill. Okay? I mean, if you don't understand that, let me show you this. I don't think that you actually have a page in your notes for this, but let me add it in. Think about a bicycle. Whatever, pretend there's a person on it. Right, here's the pedals. All right. So when you pedal a bike, you push on the pedals, right? The pedals create torque and turn this wheel, right? Because of the chain moves this thing, and this provides a torque. So torque is delivered to the wheel, causing the wheel to rotate this way, right?
Yeah.
Now, if it's icy, the wheel's going to just spin, and you're not going to go anywhere, right?
Yeah.
So what does friction have to be doing to the tire to prevent it from sliding? Is it? No, because there's no, there's no. Yeah, which way does friction have to push, you guys? It's got to push this way, right? Does that make sense? Right? Because the wheel's spinning this way, so to prevent it from sliding, friction pushes you forward. If that doesn't make sense, when you walk, you're pushing backwards on the ground pushes you forward. Friction pushes me forward when I take a step. When you pedal, your wheels are pushing backwards on the ground, just like you push backwards on the ground when you walk, and the result is friction pushes forward. Follow? Okay? We're not done, but I want to get Ethan's question. What do you got?
The front wheel, how come is that really going?
That's exactly where I'm going. So before we get to the front wheel, is everybody good with the back wheel? Okay. Now, what's the force that makes, what's the torque that makes this wheel spin? It comes from you pedaling. It comes from the chain, right? Now, why does the front wheel turn? Because of friction between the ground and the tire, right? But it's got to spin the same way, right? And the only force making this wheel spin is friction. So which way does friction push the front wheel? Isn't that wild? Okay, so the idea is it's the friction between the tires and the back wheel that push the bike forward. And then there's a smaller frictional force on the front tires, which makes the front tire spin at the same velocity as the back tire. Cool? All right. So, about this pivot point, there are two things providing torque. You pedaling and friction. Which one's got to be bigger? You pedaling, right? But there's enough friction to prevent it from sliding, and it slows down how quick the wheel would spin if friction wasn't there, right? It's providing resistance. It's working against you, right? Make sense? All right, the exact same thing is true of a car. I just chose a bike because I thought it was easier for you guys to picture where that torque comes from that makes the bike go. Cool? So this is kind of the same idea, right? If the wheel is rolling up the hill, if the wheel is rolling up the hill, for it to slow down, so the wheel's spinning this way, right? For it to slow down, the force of friction has to be up the hill, which is weird. Hello? Questions? I'm getting a lot more blank stares than I've gotten in the last little bit. Are we good? Okay. Cool. Shoot. I'm going to answer here, but I'm worried. I remember writing this when I was on the plane. Oh yeah. Okay. Good. All right. So this is. I was worried that what I had written was wrong, but now that I look at it again, I think it's right. Okay. So here are the two explanations that I jotted down, and if either of these help you, great. All right. So explanation number one: the maximum height reached by B is less than that reached by A, because for A, all of the kinetic energy becomes potential energy, because the ramp is frictionless. For ball B rather, all of the rotational kinetic energy stays rotational. So only the translational kinetic energy becomes potential energy. Cool? So that was one explanation. And then the other one is what I was talking here about friction. Yeah, so I think that just says the same thing I just said. The reason I wanted to point this out is that I think this is the only place in the notes where I actually wrote this down. Friction is not doing work okay? Because there's no displacement at the point of contact. So that is worth writing down. When something is rolling, friction does not do work. Because there's no displacement at the point of contact. Basically, all friction is doing is converting, I guess it would be converting, well, some form of energy to rotational kinetic energy, depending on how you think about it. Cool? All right. I feel like we just did a bunch of stuff. Yo-yo. We don't have time. Maybe we can do the yo-yo in a day or two. That's one of those like real specific things that's in the book that I don't know if it would be on an AP test anyway. Oh no, it is. I remember seeing that. Darn it, we do need to do that. All right, let me show you, since we're kind of having a concept-y day, let me show you one last concept-y thing. And then tomorrow or Thursday or one of these days, we'll talk about the yo-yo. Real quick, you guys know, at this point, you know enough to solve pretty much everything in your homework except for the yo-yo problem. There's one yo-yo problem, okay? So for that, the first chunk of the homework assignment, I think it's 10.1 to 10.3. You guys know enough to do all of that except the yo-yo problem, okay? Cool? All right, so tomorrow I'll try to give you guys some more examples and that kind of thing. All right, let me talk about the spool. Let's see if I can do this. I've never explained this before, so kind of bear with me here. All right, so what I've got here is just a spool of rope. I probably should have found a bigger one, but I didn't have time. All right, so if I hold the spool in my hand and pull the rope, what's the spool going to do? Which way is it going to turn? Yeah, it's going to go this way, right? Right? And if I flip it over and do it, now it'll rotate the other way, right? Yeah. Okay. Good. All right, now. Set it down on the table. So right now the spring is coming around the top. So if I pull the spring, which way will the spool roll?
Right.
This way?
Yeah.
Everybody agree?
Yeah.
All right, so let's do it. Get the spring centered. You ready?
Yeah.
Cool. All right. What if I flip it over so the spring's on the bottom of it? Which way is it going to go? Left or right?
Left. Left.
This way?
Yeah.
You ready?
Yeah.
Oh no, it fell. First with gravity. Which way did it go? Before it went down, which way did it go? It went this way. All right? So. So let me show you again, just so you can see it again. It's totally counterintuitive, but there's a reason for it. I'll see why in a minute. All right? So I'm going to pull it this way. All right? It's so weird, right? Okay? So, here's the crappy reason for why. Which way is the net force? That way. So it moves that way. Alright? I'll give you a better explanation in a minute. Alright? Now, what I'm going to do now is instead of pulling this way, I'm going to pull up. Now it'll go that way, right? Okay, so here's the deal. Here's the spool. Right? Here's the point of contact. So imagine this dotted line. If you draw a dotted line that goes through the point of contact and is tangent to the surface of the inner spool. Oops, that's supposed to be tangent to the surface there. All right? It turns out if you pull in a direction that falls below that dotted line, look, here's my pivot point. Here's my radius. Which way is the torque? About this pivot point.
Right.
That way, right? It's going to make it rotate this way. That's why it goes that way. Follow? Whereas, if I pull above this line, now my torque is the other way, right? So it causes it to rotate the other way. All right? So remember I talked about the fact that the book always uses this as your pivot point? This is a great example of one where the point of contact is your more important pivot point. Follow?
Yeah.
Okay? Yeah. And what if you pull on the line? Great question. I've seen conflicting reports on this. Some books say that it will just spin in place, and some books. So that seems like it's not too far off the report, and then, or off the truth. And then I've seen some books say that it'll just move this way without rolling. So I think there are some variables there. I think it depends on the frictional force.
We have it in the back.
So. Sorry? Okay, yeah. So that first assignment, 10-1 through 10-3, Thursday or Friday? Okay, let's do Thursday. Have a good day, guys.
Oh wait, the Jacket kids aren't gonna be here.
They know I have these.
Oh, okay. Okay, we'll talk tomorrow.
It's ceramics, okay?